Good afternoon. So we have two more lectures to go. So the exam will be next Tuesday, but double confirm the date. I believe it's 7 p.m. Okay. So hopefully today we will finish this neural network introduction, and then we move a little bit towards the convolutional neural network. And hopefully we will have some time for the during the last lecture for some quick review. So last class we see this neural network, and the question is, we know it's powerful, it's useful, how to train it, okay? So basically at the end of the network, you expect some loss function, some objectives, okay? And then using that objective to adjust, to do some kind of, we call backpropagation, or we try to adjust layers of those parameters, okay? So in our specific example, we will try to introduce this loss function. Okay, so you can try to corresponding what do we have here. You think about this is a network output, but now you will say, hey, this output need to minimize its distance between some of the ground truths. So the F sum is your network output, okay, and you want to minimize the difference to your ground truths. So you create some error, and you want to minimize this error using what? Using gradient descent. Because of the deep learning or neural network, usually we will involve a large amount of data. So the typical gradient descent is not very feasible. The reason is because the typical gradient descent asks you to compute one update after you see all samples. So for example, you have 1 million samples. You need to compute one gradient for each sample, and then compute one aggregated updates to do a gradient descent or gradient ascent. Okay, so we think this is not very efficient. What we do is we introduce some stochastic gradient descent. That means you can start to do updates after you compute every gradient from each single sample. Okay, of course, because this is not the aggregated version, given your training data may have outliers, may have some, I mean, it's not perfect. So as I say before, you go straight line. Now you are go in a drunk way a little, but to essentially do what towards. Sorry, the direction is wrong. So we go to in this direction to reach the optimal. Okay, so we go in a little bit drunk way to reach the optimal. Okay, so the compromise of these two is in the middle to do batch-wise gradient descent. Essentially to say we now will not look at all samples, but we will look at a small patch or small batch of those samples. So we basically divide our training sample into something we call mini batch. Each batch will contain, for example, 100 samples or 200 samples. Then you compute one gradient from this small batch, then create one update. Then we introduce this chain rule, because now we are like to update your parameters, which probably far away from your goal. Because before, you remember, when we create this kind of mean square error, we are always tuning or compute a gradient for some parameter involved in that step. But now think about this network. So for example, if I have an error function here, but how do I using that to adjust my weights associated, let's say, with a link here? It's a far away, right? It's not, they are not talking directly. So they are talking indirectly. How to do that? We are trying to create kind of chain rule. To start with that understanding, let's think about how this arrow will start to talking, let's say, with a weight here. Then we will talk about how to talk with a weight here. So essentially the philosophy underlying is very similar. Just think about if I want to using an arrow turn is my objective function to to compute the rate of change with respect to a particular weight, Wj. Okay. So since I do not directly talk to Wj, so I will say, hey, what will be the intermediate? What are those factors in the between? Instead of I directly look for the rate of change with a particular parameter, I will try to first look at the rate of change with respect to f sum. This is your weighted sum sent to an activation function. So because the f sum is directly part of this your arrow, so they are directly talking to each other. So then I will look at what's the rate of change of my f sum with respect to sum. Okay. Then I will look at what is the rate of change of sum with respect to Wj. You can start to see the Wj is coming to the picture. Okay. Of course, here it's not so necessary to using this kind of chain rule to think because you can directly using your calculus. But then this becomes necessary when you have multiple layers of the neural network. Okay. So one takeaway message is, first of all, remember when your fx is a sigmoid or is a logistic function, and the derivative of the logistic function can be written in a very compact form as a logistic function itself multiplied with 1 minus this. Just remember this. Or if you feel interested, you can go back using a paper. It's easy to prove this. Okay. So if you remember this fact, the derivative of a logistic function can be written in terms of logistic function itself. So then this middle term will be simplified into this guy. And the first term is very simple, right? Because you just take 2 in front, you will get this. And the last term is very simple because the sum is just a Wx. So if you take respect of the Wj, you will get Xij. So because it's a linear relationship there. I hope we are all fine with this step. Okay. Are we fine? Any questions about this part? Are we okay with these slides? Okay. Yeah, just stop my, because this is one of the more math part. Yeah. So if you have any questions, please stop me. I can go through again. Okay. So this is a pretty much summarize what we have discussed so far. But one critical fact to see that if we compute this equation is exactly the same thing here. We just move there. But one thing is try to pay attention is if we want to compute things for Wj. Wj is a weight, right? Is a weight associated with some of the age, just right before the output nodes. So for every of those age weight, they share the same factor for this part. So you just need to compute this once, and you do not. Then you use that to compute for each of the Wj. So just compute once. Yeah. So this is actually this shared factor is important because as you see later, hopefully you will enjoy after the next few slides. You will start to appreciate this fact. A lot of things are shared. Okay. So after you compute this, and then we can. This is essentially what? This is essentially the rate of change of the arrow with respect to Wj. So we compute this, we can using gradient descent to minimize our arrow. So how to do that is simply use your current Wj. The Wjt, that means your present Wj. I use that to minus this guy. Minus this guy because there's a minus sign here, so we get a plus. That is 0 xij, and this alpha here is your learning rate, how fast you want to, or how big you want each step to be, because when alpha is too large, remember, if you are too greedy each time update too large, you may diverge. You may jump here and there. Okay. If the alpha is too small, you might working like a snare, too slow, and but eventually it will converge. But sometimes you do want things converge in a reasonable speed. So usually the alpha is you need to carefully pick them, not too large, not too small. Okay. So this is how to update a particular WJ. I think that we covered this. I just, since this is a little bit math here, so I just compute this one more time. All right. Any questions? So when we have a more complex structures, for example, now, before we are talking about if we are, the arrow is here, the WJ is one of these links. Okay, so they are kind of connected, but because of the, you have activation function, you have the weighted sum, so they have a few intermediate steps. But now the problem is how do I let the arrow to control my updates about this link? All right. So we just carry on the philosophy we just introduced to using to propagate further. We call this is called back propagation. The whole thing is why the neural network they are become so how to say, so elegant and so easy to train nowadays. Yeah. So because of this backpropagation. So now let's see how we using the arrow to control, to update, let's say W11. Okay. So let's first see how this the whole thing start talking to each other. So now the arrow is still defining yi minus f W1 H1 plus W2. So that essentially to say this W1 is this guy, W2 is this guy. So my arrow is only talking with these few inputs, right? But now those inputs are from the previous layer. So the H1 is what? Because the H1 is another layer of weighted sum sent to activation function to produce this H1. Okay, so this is a one critical point. Please pay attention. We have an input. Those input go through W1J. Sorry, W11, and summing with another X2 multiplied with W21. They will sum together and send to our sigmoid function to create H1. Then this H1 will be one of the member participating by multiply with its associated weight, then to create another layer of weighted sum, then send to activation function to produce the output. Then the output will be checked across into your ground truth to see how big is the gap, which is our error. So this is a whole flow. I hope you are comfortable with that. Are you okay with that? How the input are flowing inside this network? Are we okay? Okay, so now let's expand a bit further. So since, as I say, the H1 is come from the previous layer, so the H1 can expand it now into FW11X1 plus W21 X2, then plus W2 H1. If you like, you can expand the H1 in terms of the input, again, H3, but it's unnecessary. We're just using H1 as an example. Yeah. So I spend more words here because I just want, hopefully you can, we can go through the whole things. We can clear how this network produces the inputs. Okay. So next, everything will become a calculus. We try to compute the rate of change of your arrow. The arrow happens here. Basically, is your arrow check to your output. Okay, I want to check the rate of the change of my arrow respect to W11. W11 is this guy, so they are not labeled. They are quite remote. Okay, so how to do that? We will first see, hey, how to measure the rate of change of the arrow with respect to H1 with this guy. Okay, and then I will try to see how the rate of change of the H1 with respect to sum of H1. So basically, you do the sum here. Okay, and then I will try to say how the rate of change of the sum H1 with respect to H1. So you just see when these things propagate here, I just go back and try to see the rate of change with respect to each intermediate factors. Okay. So that is a very simply you can think about how to expand this. So you using the chain rule to do this. This is the philosophy behind is exactly the same thing what we compute in the previous slides. But now we are talking a little bit even a further guy. So this one, the arrow rate, the rate of change of the E with respect to H1, this is exactly what we compute before, right? It's almost because what we compute here is essentially very similar, because before, remember what we assuming we just have one node. So this essentially can be how we compute this. Essentially, we can borrow from the previous slides. With only one difference is that previous slides, we are talking the arrow, the change of the arrow with respect to W1. The W1 is this guy. But now we are talking with the respect of H1. H1 in the previous example is your input. But W1 and input, they are linear relations. So you take respect of one, you will get the other, right? Just think about the W1 multiply H1. If you take respect of H1, you will get W1 with respect to W1, you will get H1. All right. So because now we are take respect of H1, you will get what? You will get W1. And this delta 0 is essentially the same thing as before. All right. Are we okay with that? Yeah, please just stop me if I do confuse you. Are we okay? Just so far, are we okay? Yeah, just try to follow my words, the flowing. I know this is not an easy concept, but it's actually pretty straightforward. Yeah. I will try to repeat once. If somebody feel you are too completely lost, then just ask me. I will go through one more times. Yeah. So then the rate of, you compute the rate of change of the H1. What is H1? Well, H1 is you are doing a weighted sum of these two guys using these two weight, then send to a sigmoid function to get H1, right? So basically you take a derivative of H1 with respect to the sum this. Essentially you are computing the derivative of a sigmoid function, right? The sigmoid function is essentially the same as a logistic function. But when we are talking about the activation function, we will mention sigmoid function. Okay. So we know the sigmoid function, this step is just a what? It's just a fx multiply 1 minus fx. Okay. So we didn't expand it. We just put a derivative of a sigmoid function here. Then the last term is, as I mentioned, is the weighted sum. So the weighted sum of this guy with respect to W11, because W11 multiplied with X1 is a linear relation. If you take respect of W11, you will get X1. So you will get X1. Okay. So also everything here is everything here will be shared when you compute for this layer, for this two. So you just compute that once, and you just put it. Okay. So in this way, you get a way how to compute the rate of change for this guy in terms of the final error. So this is a creative way to talk distantly in your network. So you can do this for even many layers. So now we are talking about 100 layer. So you can just carry on this process, essentially exactly the same thing. Yeah. But one cool thing that you can think about that is, how to say, this is what we just described is essentially the backpropagation. Okay, so it allows us to train many layers, like 100 layers of neural network. So here, as we can see, we have two paths. We have forward path and backward path. The forward path is much easier to understand. It's like you have a input, right? You multiply with the associated weights, and then you merge them by the summing them at each hidden node, and send to activation function to create an output. Then this output will send to another neuron in your next layer, and then you do this. This is a we call forward pass. Okay, and then the backward pass is only happen during your training. The feed forward pass happen during both the training and testing, because you feed forward and you have arrow, you back propagate to update those weights. But during the actual usage of the neural network, you only do the feed forward. You just put in your input, and they ask the network to give you an output. Okay. But during the training, because you at the beginning you don't have an optimal network yet, you want to adjust those weights. Okay. So you need to do a forward pass and see what the network output is, and then using that network output to check with what is your ground truth. What is the actual value you want the network to produce for you? You just see what's the gap in between, and using that arrow to backpropagate, right? Because we just see two examples. One is the first example is how to backpropagate your first layer to say the weight. But now the second example to say, hey, if my network have more than one layer, I have two layers, how to update the indirect links. So this is a all this called backward pass is what we actually using is something we call backpropagation. We're using a chain rule. The chain rule is say, if I don't have a link with you directly, let's say you have an arrow at your output node, but now I want to update a weight far away. So what I do is I just try to see, I just try to check all the factors which are related. So basically, I just try to make, in order to compute the rate of change with another weight, which is not directly associated with your output node, we just try to say, hey, the rate of change with each intermediate component, then multiply them together to become the rate of change with respect to a weight which is far away. So any additional clarification you want me to add? I'm sure some people may lost. The first time I hear this, I get completely lost. So let me know which part you didn't get, or which part, or you completely get lost. And both is fine. You can raise hand and just signal me and let me know. Are you okay with this? Oh, okay. I see somebody say, okay, I'm very happy. Yeah. Okay. So in fact, you just, if you're comfortable to force yourself to believe this chain rule, then things is become pretty straightforward. And there's one more thing I want to say, but I'm not sure how straightforward to mention here. Let me see. looks like I don't have a clear the equation there to say that. But one thing I want to make you be aware is when you backpropagate, you will actually find is that the arrow are weighted by the age to compute how the age, how those weights are changing. Okay. So I hopefully I can find a good example to say that. So probably this is this part maybe is relevant. So for example, when you backpropagate, as you can see here, is actually this delta 0 is shared, right? It's common for each of them. But when I push towards the H1 side, actually I weighted by the W1. I mean, it's sufficient for you to get a flavor there. So which is the reason why when do your backpropagation is super efficient, because you are computing something and then this is shared for a couple of weights, then you just weight it according to each weight, then that will be the factor you are going to use. So when you do backpropagation, it's not as complicated as you thought. It's almost as efficient as your do feed forwarding pass. All right. It's sufficient just to get a flavor of that. All right. So I believe you, since if you have already done the homework 10, you know how this work. So basically use sklearn, you can import some simplest, because the sklearn doesn't increment a very sophisticated neural network structure. If you really want to use that more seriously, there's things called PyTorch and TensorFlow. I think in the last set of lecture, I will briefly mention some example about how to use, not how to use, some examples from PyTorch to create a more complicated neural network. Okay. So the good things is about PyTorch and TensorFlow, they are free to use, they are very easy to use, very powerful. So the multi-perception network, I'm sure you already have used this to classify these three class problems. So this is essentially the simplest multi-layer network. I believe you have done this. You just create a multi-perception classifier and fit your data. Then you probably set what is a number of layers, what is how many neurons, what is number of gradient descent updates, and I will talk more, because before we have these parties, because we don't have the next lecture. But during the next lecture, we will see a little bit more about the training part. Okay. So again, before that, we want to say during the deep learning, usually you do not have a very good optimization function in terms of the convexity. Because as I mentioned, if you're using gradient descent to look for a minimal, global minimal, you need your function to be a convex, like the bus tube type. You need to have a very beautiful this type of shape, right? So then you can know, hey, there's a lowest point there. But if you have a function something like this, there's a lot of local optimal. So this is a case for deep learning. We know for deep learning, usually you have a lot of local optimal. So it's not necessary you will find which one is better, okay? So when we are using this mini batch version of stochastic gradient descent, it's not guaranteed we will converge to a global optimal. But in typical, it's okay because we found many those local minimal for neural network, they are pretty good, okay? But we want to speed up. As I mentioned, since it's difficult to look for the alpha is the step size, right? When we doing this, you need to decide a value alpha. The alpha can be 0.1 or 0.01, 0.001, because you just heard from the lecture, you can't set the alpha too big. Let's say alpha equal to 10, 100. You will not converge, because typically if you set a too large alpha, you will see your loss function actually increase. You don't really, so you have to pick a small enough alpha in order to make it slowly converge. But if it's too slow, you will wait for weeks for your network, for your model to finish training. I'm seriously, because when my students they are doing a experiment, usually it takes probably a week for the experiment to converge when you're using a lot of data. So you don't want to really to even slower, right? You don't want to wait for months to complete one experiment. So how to do that? Then we have different ways. We have a couple of different ways. For example, something, let's say, called a dam optimizer, or those are some additional techniques, or something we call momentum. There's a lot of different ways we try to make your convergence behavior to be a little bit stable and faster. Okay, so let me quickly move to the next. So far, we're okay with this backpropagation. It's one of the most confusing topic. But yeah, feel free, because we still have one more classes. If you have a question, feel free to raise. All right. So this will be the last. This will be the last actual lecture. Okay, and since we don't know, we are able to cover this today or only do that during the Friday. So we discuss among three instructors among us. We decide to not including material from this lecture in your exam. So this is like, but great, nice to hear, but it will not be tested. But I bet you like to really hear this, because this is some big deal. Convolutional neural network. Essentially, when we use neural network, we do not use this fully connected network, like a multi-layer perceptron. It's good for homework 10, but it's not something we actually use that more heavily. So this is a good topic to know, although we will not test about put any question about this. Are we clear? There's no question will be designed for this lecture. Just only for this one. Yeah, the neural network still will be tested, but for the convolutional neural network, what I covered next will not be on your exam. Okay. So this is a convolutional neural network. They come out, especially at the beginning is more for the purpose of image processing. Yeah. So this is there's around year 2010, 2011. So there's a couple of papers they published by doing some we call ImageNet challenging, and suddenly they're using neural network. They dramatically improve the performance. So people start to re-put how to say they have renewed their enthusiasm on this topic, because before that, for almost about 10 years, people will feel very shy about talking they are using neural network for anything, because people just in general already believe neural network probably sounds like an interesting idea, but maybe it's not useful. Okay. But then after some people show, actually you can work greatly using a neural network to improve some very difficult image classification problem. Then this is a new wave of deep learning comes. So how to do image classification using neural network? I believe in homework 10, you already see the general idea. So you will start with collecting a huge amount of image, really huge amount of image. Okay, if you only have a very limited, like your homework 10, you have a very limited. That will, if you're using neural network, you will have an overfitting problem. Okay, if you have a really huge amount of image data or image data, then what you do is a very tedious. You need to label each of them with an actual class label, like a cat, dog. You need to label each of them. Okay. So after you doing this, you will try to partition your data. So now become compulsory to say you need to have a training, validation, and testing. Yeah, so I think that I mentioned this during some of the classes. At the moment, it's okay. We just say training and testing. But now you do need to have a training, validation, and testing. The validation considered as part of your training. Yeah, okay. And then you are using your training data to adjust layers of your parameters. Sometimes you need to using validation data to decide how do you want to, what to do with your some of those hyperparameters. At least there's two very important hyperparameters here, which is first is your learning rate. Basically the alpha, right? The alpha, you can simply, during, for example, exam, if you really see a learning rate, usually we're assuming a single value, let's say 0.1, 0.01. But actually, when you during your real training of your neural network, there's no constant alpha. The alpha can be used for a while, then can be keep changing. So, for example, every 100 iterations, you reduce your alpha by 10. That is or there's a more sophisticated schedule to how do you reduce your alpha. In general, you like to reduce your alpha every while to reduce, because you want to start with a relatively large learning rate, but then keep reducing it. So this alpha is one of the hyperparameter you have to pick probably from your validation data. There's another hyperparameter which is your regularization strength. Think about your ridge regression, right? You have your when you do linear regression, you are putting a W L2 norm. You're putting a square of this your W2. The weight you want to regularize your weight. You put the lambda there, right? The lambda is your regularization strength. Okay. So here is essentially the same thing. You want to training your network, but you want to minimize the overfitting. So you want to regularize it. So you have some kind of lambda there. So those things are the what you need to fine tune using your validation data. Okay. So after the training, after you really adjust 100 layers of neural network, then your network is supposed to say, taking let's say a cat image, it should to give the highest response to the cat category at the output. So from the output, you will see the cat category probably has the highest probability. Then you will say, hey, this is a cat. So this is a general how this neural network works when you do object recognition. Okay. Do we get the big picture how this works? So now, in order to process the image, I mean, image is like using a phone to take a photo, then you have an image. But actually, if you look into those pictures, you will see they actually each if you open an image with your notepad, you see a lot of values, right? Those values is usually between 0 to 255. Each of the points, they are represented by some values. Okay, of course, if you have colored picture, you will have 3 channels. We call RGB, red, green, blue. You have 3 channels. So you are coding things as 3 big matrix of numbers. So you have 3 channels. But if we are only talking about grayscale, like basically you have 1 channel, and each value still from 0 to 255. So each of the points, we call it a pixel. So here, of course, looks like for simplicity, we try to maybe normalize those points between 0 to 1. You don't need to do that, but you can do that. So then in order to using neural network, the typical way is you first vectorize it. No matter how you try to put your images into a vector. Okay, you do a column layer, column-wise stacking or row-wise stacking, whatever. You have to put them into a vector. Okay, then those vectors, each of them will consider as an input to a neural network. I believe this is probably pretty much what you did during your homework 10, right? So actually you are doing something like this. Okay, so this is what we call fully connected. So basically, each pixel you are associated with many weights. If you have, let's say, four latent nodes in your signal layer, so basically each pixel will have 4 nodes, right? So if you have a super tiny image, then this is okay, right? But if you're talking about, let's say, a 4K image, even had the first layer, I guess you already be filled with too many weights. Do you see that? This is because those weights are grows too fast. So this is not a great strategy to processing images. All right. So as I put here, the density of the connection between layers increase intractably as the size of the image increase. So one very clever way or very elegant way to do this is try to adopt 2 principles. One is called local connection. Then the other one is called weight sharing. So what we do here is essentially you try to change the fully connect strategy into the following. So each node, now we only process some inputs from a local region. For example, each node only process a 6th node in some kind of local region. Of course, how to define the local region, we will talk about the next slides. Yeah. We need some meaningful local region. So, but essentially now, each of the nodes only need to take care a small portion of the inputs. Okay, so this is called local connection. Then the weight sharing is to say those hidden nodes or those neurons, using a more a cooler name, those neurons, they will share weights. I mean, neurons from the same layer, they are allowed to share weights. So basically now, those 4 nodes or 4 neurons, they are reusing the same set of 6 weights. So just counting about, I don't know, maybe here it has, let's say you have a 10, I don't know how many, probably 10 nodes here. So each of them, you have like 40 connections. But now we only need 6 weights to define the current first layer. Are we okay with that? So think about this. If you are if the input nodes increase dramatically, this strategy will be super compact. All right. But this is not the end of the story. This is just the beginning of the story. And this is a cool, the best part is that by using this local connection and weight sharing, if you are smart enough, if you are able to imagine some kind of special perspective. So this is equivalent to what? Equivalent to say, I have a block of share weights, and I just take this block of share weights and convolve with my image. Think about it. So now, this one is trying to say each nodes, each neuron will only take care of local inputs, and those neurons will share the same set of weights. So now think about those share weights to be in the form of a block. And now I will take this block. I first at the position 1, and I will try to do I take those region with corresponding size. I will take this region and doing a dot product. Basically, you do a weighted sum. Okay, and then you move your block to the next position. Then do the same thing. You will take another block, do a weighted sum. So this essentially, it looks like you are sliding your shared weights across your image. At each position, you just take that local region inputs and do a dot product or a weighted sum, then generate output. So this is essentially is doing the same thing, right? Because we have a shared weights and go through your input. At each position, you are generate weighted sum neuron output. Do we see that? So this is reason why we call this neural network a convolutional neural network. Okay, so this essentially you are sliding a block of weights across your image. Yes, there's questions.
So is there any benefits to not do local so when you were saying you're using local, like you're only using 6 different vectors as opposed to all 10?
Yes.
Is there a benefit to using all 10?
Yeah, of course, because now you only need, if you want to, you don't do local, my share weights now need to corresponding to the whole image size. But now I only need to be 3 by 3 because I only want to take care a 9 input for that region. So I can have a very tiny, remember those this is those W's, because those are the weights you need to train, you need to learn from your network, from your data, right? We just learn the backpropagation, those, we are training the weights. So those weights, if they are small enough, will be much easy and stable to learn. If they are too huge, then probably require a lot of data to learn. So here we just have like a 3 by 3 by 3. We only have like a 9 coefficient to be learned. So I'll probably stop here, and during the last lecture, I will try to finish this and then just try to see is there any questions from you guys.